In this video, we're going to talk about normal and tangential coordinates, which are sometimes called path coordinates. And these are very useful when you're looking at things like planes, trains, and automobiles, as well as in this video of a motorcycle driver. So they're going around a curve, then they're in a straight path, and now you can see we have a small accident, and you have to be careful if you're a bystander. This type of coordinate system is used all the time in civil engineering applications when you want to think about the maximum safe speed, and what we end up doing is defining the tangential direction as basically straight ahead, where your velocity is going. So if I'm on this cloverleaf, the tangential direction is going to be straight ahead, and the normal direction is going to point inwards towards the center of curvature. We can look at things like trains as well. As we're going around a curve, we don't want that train, of course, to end up derailing. The lesson objectives for today are, first of all, to know that anytime you're moving in a curved path, you have an acceleration towards the center of curvature. The second is to determine when to use path coordinates versus the polar coordinates we'll talk about in the next video, and Cartesian coordinates that we talked about in class. And then finally, I want you to be able to use path or normal tangential coordinate systems to solve kinetics problems. So as we mentioned before, how we define this is if I'm going along a line that you can see here in the blue, then my tangential direction is just tangent to the curve. It's basically straight ahead, whatever my velocity is pointing towards. The normal direction now, you can think about putting a big circle right in here, okay? And the radius of that circle we will call the instantaneous radius of curvature. Okay? And the smaller that is, or the tighter the curve, the higher the normal acceleration is going to be. And we'll talk about that more in just a moment. And once we've learned how to define these coordinate systems, sometimes we'll see them as u sub n, which is the normal direction. Most of the time we'll call it e sub n. Okay, same thing here where it's u sub t, that's going to be the tangential direction, right, which is just tangent to the curve or the path, and then the normal direction is always going to be perpendicular to that tangential direction. And we can see something similar here. So if I'm at point A going around here, the normal direction is pointing in towards the center, and this is tangent to the curve. Down at this point, the normal direction would be up here, tangent this direction, and then finally at point C, you'll notice that the normal direction kind of flips sides of that curve, right? Because now my curve is going this way, kind of a concave down, and the tangential direction is still, of course, tangent to that path. Okay, so let's do a quiz. If a particle, like a car or that motorcycle you just saw, is traveling on a curved path, then the tangential component of acceleration, A, depends on the radius of curvature of the path, B, represents the rate of change of velocity of the particle, C, will be positive if the particle's speed is increasing, D, never changes direction, or E, is perpendicular to the direction of travel. And the correct answer there is going to be, will be positive if the particle's speed is increasing. Because if we look at B, that's the other one that's a little bit tricky there. It says it represents the rate of change of velocity of the particle. And that's not quite right because velocity is a vector. So if that had said represents the rate of change of speed of the particle, then that actually would have been correct. And that's a fairly subtle point. These are the expressions that we're going to use where the velocity vector v is really just defined as the speed v sub t in the e sub t direction. Okay, so that's just whatever speed you might see on your speedometer in your car or on your little computer that might be on your bicycle. So whatever that speed is that you're measuring, that's going to define my velocity, and that's my direction. The acceleration now can be expressed as the time derivative of that tangential velocity, this v, and that's going to be in the e sub t direction. And then we add to it this normal. So this is a v squared. These are the same v here over rho, which is that instantaneous radius of curvature we discussed and that you read about. And that's going to be in the normal direction. Okay? And the other way I can write that v dot, that's just the time derivative of that speed. And you can see that right here. If a particle moves along a curve with a constant speed, then its tangential component of acceleration is positive, negative, 0, or constant. So if it's not increasing its speed, that means that tangential acceleration is going to be 0. The normal component of acceleration represents A, the time rate of change in the magnitude of the velocity, the time rate of change in the direction of the velocity, the magnitude of the velocity, or the direction of the total acceleration. And the correct answer here is actually the time rate of change in the direction of the velocity. Okay, because I was going in one direction, and then as I go around a curve, I change that direction. So that's really what the normal acceleration is all about. It's about changing the direction of my velocity. Okay, A would really be the time rate of change in the magnitude of the velocity. That would represent really more your tangential acceleration. More applications, right? Certainly amusement park rides are always there. So whichever direction you're traveling in, that's going to be the tangential direction. And then the normal is going to be in towards the center. So certainly you have to make sure that you're not causing too large of a normal acceleration that would make people pass out or injure them. What we can do now is just apply Newton's second law to any of these types of problems. If I draw a good free body diagram like what you see down below, and these are going to be real forces. So it could be like a tension in a rope right here. It could be some sort of a acceleration of a car due to friction and traction on the tires. It could be some sort of a normal force due to the bank of a curve. Okay, so now these forces, whatever they add up to be, are going to equal these inertial terms. So mass times a normal acceleration, which of course we have right here, as well as a mass times a tangential acceleration, which we have here. So this is very similar to what we talked about previously, where we could look at the sum of forces in x equals max, or the sum of forces in y equals may. So if a particle is moving at a constant speed along a curved path, then the net force in the plane of motion acting on the particle is equal to 0, points to the center of curvature, points outward from the center of curvature, or has an unknown resultant direction. And this answer is going to be points towards the center of curvature. Okay, when analyzing the tension force in the chains of a chair swing, the free body diagram contains three forces: gravity, the chain tension, and the centrifugal force. So is this true or false? So this is going to be false. Remember, there's no such thing as centrifugal force. I need to have some sort of force, like the tension in the rope, that accelerates me towards the center of curvature. So if we work through a full problem, where in a carnival ride, chairs swing about a vertical axis with a constant angular velocity, so the swing rope is inclined at 65 degrees to the vertical, as shown here. The rope is 40 feet long, the combined weight of the rider and chair is 180 pounds, and the weight of the rope can be neglected. Determine the tension T in the rope and the linear velocity of the chair and rider. So the first thing I want to ask you, is this kinetics or a kinematics problem? Since we are caring about forces, this is going to be kinetics. And since it's a kinetics problem, my first step is to draw out my FBD and my KD. So what forces should go on the free body diagram? Hopefully you talked about the tension in that rope or in the chain, and then also the weight of the rider and chair. So those would be our two, and we add in our dimension of 25 degrees. In which direction is E sub n? Which direction is E sub n point? So sometimes people will make the mistake of putting it up in that T or tension direction, but it's really in towards the center of the path, right? So this is going around a curve, so this is going to go in towards the center of where that is. So it really doesn't matter in this case if I was at 65 degrees or if I'm lower down. I'm always pointing just right in towards that axis here. Okay, so I'm pointing inwards, not along the rope. Okay? Then this direction vertically we can call either E sub B or sometimes we might just call it E sub y. It really doesn't matter too much. Okay? But that's also going to be 0 if I'm just going around at this constant angular velocity, and that's saying that I'm not moving up or down. And then finally, I need to draw in my axis or coordinate system. And then this is solved out online for you. So in this animation, we're going to show you a few different things. The first is to remember again that the direction of velocity is always tangent to the path. So this could be like rolling on a roller coaster. So this blue arrow here, the V, is going to show us which direction our velocity is in, and that's going to of course be E sub t. This green vector that we'll see is going to be pointing in the overall acceleration direction for this car that it's going through. Right? So if we watch this for a little bit, we can play it. Right? And you can see it's moving, it's starting to slow down. So I have something going against, right, the minus this v direction or E sub t, and then it's got a little bit of normal direction as well, right? So I have a normal direction here, I've got a backwards v direction there, so the overall component is going to be in that direction there. Okay? Then as I start going around that curve, you see that gets really big around here, because that means that rho term right here gets super small, so that means this gets bigger. So now we're going to see that this is going to get faster, right? So as I go and I'm going down the hill, I still have a acceleration in the normal direction here, but I'm speeding up as I go down the hill. So I'm going to have a normal direction going this way and a tangential direction going this way. So I can continue playing this, and you can see I'm speeding up. Okay, now that the curvature is changed, right? So now the center of my curvature, right, is up in this direction. So I am speeding up, so I have one component in the E sub t here, and I have another component in the E sub n there. Okay? And then basically I can follow this as I go around. And now again I see that here's my curvature going, so the acceleration vector is going to point down in this way, and then we can watch it as it finishes up. So finally, you've got one more example problem that's looking at a race car, and it starts at point A right here, and it's going to speed up according to that relationship where AT is equal to 0.6 minus 0.002 v squared. So what would the 0.6 correspond to physically? What would that come from physically? It would basically be talking about the force of the car going forward, so the friction or thrust force on the tires, and then 0.002 v squared really represents the drag. So what you need to do is ask, what is the velocity and acceleration of the car when it reaches point B over here? And you should recognize that it's going to have both a tangential, so it's going to have an AT going in this direction, and it's going to have an A sub n pointing towards the center of the curve. So you're going to need to use this relationship up here to figure out what that tangential velocity is once it gets to point B. So if you have any questions or any comments on how to improve this video, please enter them here, and I will see you in class next time.